Good morning, everyone.
Morning, Miss.
Morning.
I gave another minute for those who are coming in, then we'll start with the prayer.
Okay, please settle down. Settle down. Thank you.
Okay, share screen. Okay, so we'll be starting now with the topic on conduction. For this meeting, it cannot be finished, of course, because we're only given an hour here. But we'll finish the first two of the 4 types of heat transfer by conduction. So let me present the conduction slide. Okay. So what you'll be seeing here is the general Fourier equation that tells you of the rate of heat transfer. By the way, class 1. Excuse me, why is it not showing everything? Okay, so that I think that's better. So for Fourier's law, you're given the rate of heat transfer here, the Q with the dot, meaning it's measured per unit time, and it's the product of the thermal conductivity constant, which is a characteristic of a material. Then you have the cross-sectional area perpendicular to the direction of heat flow. Then we have here the rate of change of the temperature of the object measured x distance from where the transfer of heat is commencing or starting from. Now, as to the different units of these particular parameters and variables that are appearing in our formula, you have it here. So if it's in English, it's BTU per hour for the Q. And if it's in SI, it's in watt. So you have here the corresponding set units for thermal conductivity in SI, and this one is for English. As for the X, which is the X squared rather, which is the area of the heat transfer perpendicular to the direction of flow, which is in meters squared or feet squared. And your temperature, of course, since it's in absolute values, it should be in Kelvin or it should be in Rankine in English, Kelvin for SI. Now you have here the different conversions that you might find useful when you are converting the set units of your thermal conductivity, the heat flux, the heat transfer per unit area, the power, and for the convective coefficient later on, which is H. When we go to convective mass transfer or heat transfer for that matter. Now, we continue. Let me see if I can also show you everything in this slide. So when we speak of conduction in gases, so this is the mode of heat transfer, which is predominantly by transfer of kinetic energy by collisions. So we know that gas molecules are very far from each other, and as such, the transfer of energy is in what we call the mode is normally by means of collision. Now, smaller molecules tends to move faster and have higher thermal conductivities in the case of gases. And thermal conductivities are directly proportional to the square root of the absolute temperature. So if the thermal conductivity increases, so we say that the square root of the absolute temperature of the object also increases, since the two is said to be directly proportional. So this is only, by the way, applicable to gases. So thermal conductivities in gases are independent of pressure up to a few atmospheres. So meaning at non-elevated pressure conditions, our thermal conductivities for gases is not dependent on pressure. But it's a different thing already when it's already increased pressure. As for liquid, so the thermal conductivities for liquid varies moderately with temperature based on this particular formula, where A and B are empirical constants. So you can see them in your Paris Chemical Engineer's Handbook for liquids as to how the thermoconductivity depends on the particular constant for a particular liquid. So a liquid may have a different set of A and B values compared to another liquid. And it's still dependent on the temperature. Now, just like in gases, when we speak of moderate pressures only, in liquids, the thermoconductivity is not also dependent on pressure. Now, water, a liquid, has higher K compared to organic liquids such as benzene. So meaning water absorbs more energy than liquid benzene because of its higher thermal conductivity value. Now, as for solids, when we speak of thermal conductivity of solids, so it varies quite varied widely. So varies widely in solids and very high for metals. We know this, and nearly constant or decreases slightly with increase in temperature. So this is because of the free electrons which move through the metal lattice and transmission of energy of vibration between adjacent atoms. So the transfer of energy in solid is very high because of the movement of this particular free electrons, which is free to move along the crystal lattice of a material. And in the process also, the movements of these free electrons is associated with their actually not only vibrational but rotational motion. Okay, now, so in terms of thermal conductivities for solids, this is very low for insulating or non-metallic materials, which you also know, where mechanism is by transmission of energy based on vibration between adjacent atoms. So very low in the case of insulating non-metallic materials, but very high in the case of metals. We speak of this particular thermal conductivities in solids. Now, in trapped gases in solids, if we have the presence of trapped gases in solids, this will lower the thermal conductivity of that particular solid. So if your solids have pores and there are trapped gases inside the pores, then it will lower the thermal conductivity of that particular solid. We will continue. Now, in case of one-dimensional conduction in the absence of heat source, so meaning we're not heating this particular, let's say this particular slab that we have, no, there's no heating that happens on both sides of the slab, and your thermal conductivity constant K is of course a constant, then this is our direction of heat flow. Here from T1 to T2, from a source of higher temperature or from the portion of higher temperature to a portion of lower temperature. This is the thickness of our slab, which is the delta X. This is the X direction in which heat is going to transfer to, because you could see here that your Q with the dot is in the same direction as we measure our X. Now, what about this delta X over K? Product of K and the A, this is actually the resistance to heat transfer. The resistance to heat transfer is this particular set of variables and parameters. So you have delta X, the thickness of our slab, A, the cross-sectional area perpendicular to the direction of heat transfer, and K, which is a constant, a characteristic of your solid. Now, so the rate of heat transfer in this particular flat slab is given by this formula, which was shown to you in the previous slide. And, oh, sorry. I don't seem to see why there's a, and you could see that this delta T, rather this particular expression here could be written in the form of the delta X staying in the denominator and the product of the K and the A, which is here to be interpreted as in part of the numerator is written as the denominator. Just to illustrate what I have mentioned a while ago, that this set of variables and constant is your resistance, the heat transfer resistance. Let me check, class, if this is not in. Okay, so this one is not shown. I don't know why. So you have the numerator as the driving force, So again, I will emphasize that the driving force for conductive heat transfer is the change, or rather the difference in that temperature. And the resistance is in the denominator. So generally, this is how your heat transfer equation is written. In the numerator, you have the driving force, the difference in the temperature, and in the denominator, you have the resistance to heat transfer. So it's written like this. It could be written in this manner. That way, it follows this general form of the heat transfer rate equation. Okay. Now, let me minimize. So you could see in here that if you have several solids, now we call this conduction with resistances in series, and these particular solids, of course, represents different resistances because we assume that solid A is different than B and also than C. Otherwise, if they're all the same, we just can view this as one entire slab of thickness from this portion until here. But since it's labeled as ABC, we are to assume, it's just correct to assume that these are different materials. As such, your material in which heat is going to be conducted through or transferred through will be viewed as a series of resistances. So in this case, you have one resistance here in this material A. So you will have here delta XA and you have here K sub A, representing that of the thickness of material A and the conductivity of material A respectively. You will have the same for delta XB for material B for its thickness and its thermal conductivity is K sub B, and you will have delta XC for the thickness of the C material, and you have K sub C for its conductivity. Now, in this series of resistances, we view it also to have different temperatures and its boundary. So you have T1 here, we have T sub 1, T sub I1 here, this one, and you have T sub I2 here, and you have T sub 2 in here. Now, if you're going to write the net rate equation for this particular set of resistances in series, you could see, class, that you have the rate of heat transfer in each of your materials in series are all equated, telling you that the amount of heat transferred that transferred through A, through B, and through C are equal. So you can see they are all equated. Now they are a series of materials, or to be interpreted as a series of resistances. We don't view the amount of heat transfer as the sum of the heat that is being transferred to each of the materials, but rather we view it as that the heat transferred from one material to another will just be equal. So we follow the same formula that we had presented in the previous slide, and that would be this particular formula. So if you rewrite the K and the A here as a denominator for the delta X in each of these fractions, then you will have a general form of the rate equation, which is driving force divided by resistance. Driving force for material B divided by resistance for material B, and the same too with material C. Now, if we want to get the temperature difference between T sub 1 and T sub 1I, the boundary between material A and B, that could be equated to this one. So you just transfer the Ka product here below the Q, and the delta XA is cross multiplied in here. So I think you know very well your algebra by now. So you transfer it here and you transfer this one. So you have the driving force. In this case, you have the driving force for heat transfer for this particular material represented by this one. The driving force for the middle material, which is B, will be represented by Q delta X sub B over K sub B times A. Actually, in form, it's exactly the same as what you have represented here for the driving force in material A. The driving force for material C, which is the difference between T sub I2 and T sub 2, would be the same in terms of pattern as what you could see in here for materials A and B. So in here, you have the representation of the driving forces for each of your materials in series. And in here, you have the heat transfer rate for each of your materials as well in series. In here, you have the resistances. Okay, now I will proceed with the next slide. So yeah, I have copied what's written under the last part of the previous slide, so you can be refreshed in here. And if you're going to add class, if you're going to add these three, what will happen actually is that you will just have the difference of the temperature T sub 1 and T sub 2, because this one will cancel with this and this one will cancel with this. So you have on the left side the delta T, the overall driving force for heat transfer that will occur from material A to material C. Now, since you have added the driving forces here for each of the materials, you also have to add this one, the Q delta X K A set of variables and parameters. So you have this for A, you have this for B, and you have this for C. Since Q is common to the three, you can factor it out. And as such, we can see from this general form of the equation that the driving force for our series resistances is equal to the rate of heat transfer multiplied to the summation of the resistances, because we start the previous slide with the individual resistances of our materials. So now these individual resistances are being added in here. Okay, so this formula allows you to determine the overall driving force, and you have here the rate of heat transfer. Okay, just a minute, class, just a minute. Okay, sorry for that, class, huh? Now, we have here a sample problem that illustrate the use of the formulas that I have given to you in the previous two slides. So here, actually, this is snipped from our, I think if I'm not mistaken, this was taken from John Couplis. Okay, if you have a copy of John Couplis, a PDF copy, then it would be easier than having the hard copy to study, because everything is in just one reading. But what is good with the hard copy is you can go back anytime without hurting your eyes, because it's so difficult also to read a PDF copy and study at the same time. Okay, so in here you're given a flat furnace wall, which is constructed of a 4.5-inch layer of a silocell brick with a thermal conductivity of 0.08. So I will not read anymore the set units. So this particular brick is backed by a 9-inch layer of common brick, the conductivity of which is 0.8, also the same as that of the steel or cell brick. Then you have the temperature of the inner face of the wall is 1,400 degrees Fahrenheit, and that of the outer face is 170 degree Fahrenheit. What is the heat loss through the wall? What is the temperature of the interface between the refractory brick and the common brick? And C, supposing that the contact between the brick layers is poor and that a constant and that a contact resistance of 0.5 degree Fahrenheit hour feet squared per BTU is present, what would be the heat loss? So you have three questions to answer in this particular sample problem. two of which is asking for heat loss and the temperature of the interface, and the last is a condition that will also determine the heat loss again. So we'll go through to the given information and how we can apply such in determining the required unknowns. Okay. Now, so we assume a cross-sectional area of 1 square feet. Now, why the need for assuming a cross-sectional area of 1 square feet, class? If we go back to our problem, the problem is silent about the area in which heat is to pass through. There's nothing wrong with, in this case, there's nothing wrong with assuming a cross-sectional area of 1 square feet, because anyway, what you will be giving is the heat flux, the rate of heat transfer per square feet of material. So that's heat flux actually. So meaning if you will now be given the entire area of the wall, then all you have to do is multiply that particular value of the heat flux by the total area of your wall. That would then be the total amount of heat that was transferred per unit time. So whenever you encounter a problem wherein the area is not given, it's okay to assume a particular cross-sectional area. And it is suggested that you use 1 square meter or 1 square feet, whichever is applicable in terms of the units that are given in the problem. So our problem here gives it in English as the main unit, and you are also given the SI unit in equivalent inside the parentheses. So we will use the English set of unit then. Okay. Now, you have then to solve the individual resistances of your brick. So you have a combination of silica and the normal brick in that case. So you have the thickness of the silica given. Now that particular thickness, just like that of the brick, is in inches. So it's suggested that you convert it in foot, because your assumed area here is in square feet. So then your length should be in terms of feet as well. So if we go back to the problem, class, it's given here that your brick, a specialized brick, is 4.5 inches in thickness, and the common brick is 9 inches. So if I go back to this slide, you could see that you have 4.5 here for the silo cell brick, and you have this one for the common brick. And then you divide them by the corresponding thermal conductivities of the two. So for the silo cell brick, it's 0.08. For the common brick is 0.8. Oh, there's a 0 before this one. I thought they're just equal. So different conductivities between the two. So now you have here the resistances of the two. Why get the resistances of the two? Because we need to get the total resistance for our common brick reinforced by the special brick, which is silo cell. Okay, so this is your total resistance. Then we solve for the overall temperature drop, or shall we say the overall temperature gradient, or your overall driving force. That would be the difference of the temperatures of the let's say it's given here the inner phase, which is 1400, and the outer phase, which is 170. Okay, so then you will have here the difference to be 1230. You have the driving force, the delta T, and you have the summation of the resistances. So based on our formula, we have the driving force divided by the resistances. This would be then your rate of heat transfer in BTU per hour, English unit, because we're using the English units on top. Now, the temperature drop on one specific resistance is the same with overall temperature drop. So we equate this temperature drop in the silo cell brick with that of the overall temperature drop and the summation of resistances for our series of resistances, because we have two types of bricks, and we will get this particular value. So we have 1,230 for the overall driving force, the delta T, and we have 5.625 for the summation of the resistances, and we equate that to the resistance only of the single-cell brick, which is 4.687, and we will get the temperature drop within the single-cell brick only. Now with this delta T, we can get the temperature in the interface or in the boundary between the single-cell brick and the common brick. So if your delta A in this manner, in this matter here, if we get it from this particular set class, we have 1,230 divided by 5.625. And this one, inisya, kay kinahanglan ta mabalaan ang delta T, you will get a delta T sub A value of 1,025. This 1,025 should be equated to the inner face, which is 1,400, where you have the single-cell brick minus the temperature of the shall I say, the boundary or the interface. So you have 375 for that. Let me go back to the question, class. So what is the heat loss through the wall? So for the letter A, because I've been discussing, this is already the heat loss through the wall, the entire wall that is. So this is, let me annotate. So this is already the answer for letter A. So we may not get lost on what is really required. So this is our A. And then I'll go back to B so that you'll be guided on what is really being asked. Letter B, no, don't mind the A. What is the temperature of the interface between the refractory brick and the common brick? So this one now answers letter B. The temperature of the interface between the refractory brick and the common brick. Your refractory brick is your silo-cell brick, and your common brick, of course, is the next one. Okay, so this is A and this is B. Okay, now we go to letter C. Let me just clear my drawing. So this is answer for A and this is for B. We go to the C. So for C, you have a condition that suppose that the contact between the two bricks is poor. And look at this, and that a contact resistance of 0.5 occurs, is present in between these two. What would be the heat loss? So there's an added resistance to heat transfer aside from the resistances that is being offered by your refractory brick and your common brick. So this was not accounted for when we summed up the resistances based on the two materials. So what we're going to do, so we have already determined A and B here. We need to account for that particular heat loss that was stated in here because of the added resistance, which is not accounted for in the two materials. So what we'll do is, we proceed to the next slide. We need to add that 0.5 to the total resistances already. So we need to account for what we call as the contact resistance, aside from the resistances of the two materials. So you have now a total of 6.125. So the actual heat loss per square feet, so now it's being stated here that this is per square feet of pipe, is then equal to the 1,230 temperature drop, which is our driving force, divided by this new summation of resistance, which is resistances rather, which is 6.127. So this is 201 BTU per hour for the total heat loss per square feet of pipe. Now, class, this has to be really stated because when we speak of the heat transfer rate, if the area is not stated, then you have to really assume. So this has to be also stated when you answer. So it should be 201 BTU per hour. Now, before I go to the next part, do you have any question in this particular sample problem?
None, miss.
None? Okay. Then, any question? Wala good question? Sige. Now, we go to Fourier's law applied to a cylinder. Okay, what if we have a cylinder? Hopefully, we'll be able to see because it's difficult for me to, if not everything is shown. Now, I have a problem with my slides class because if I do presentation, everything is not shown. So anyway, if you have a cylinder, you can envision it at a roll as a pipe, a roll of your toilet paper, a cylinder. So you have something, a thickness of your material here and something hollow in between. Your radius is always measured from the center, and then so you have R1, and then you have R2 for the outer cylinder. So R1 is inner cylinder, and you have R2 for the outer cylinder. At any particular distance from the center, that would be R. Okay, now T sub 1 is the temperature of the inner cylinder, and T sub 2 is the temperature of the outer cylinder. So you can view two cylinders here, one inner cylinder and one outer cylinder. This same actually class is the form of our rate of heat transfer. You have the gradient here, the driving force. So that would be T sub 1 to T sub 2. You may wonder, Miss nga ang T sub 1, hindi pwede sulion, T sub 2, then T sub 1. In the case of pipes class, normally pipes are used in the transport of heating fluids. So the heating medium is inside or in the annular space in the inside of your pipe. So we view that the inner part is hotter or is at a high temperature compared to the outer portion. So we say that T1 will be greater than T2. So the direction of heat transfer will be from the inmost part to going out. So that is why you have T1 minus T2 here. Now, as to the resistance, then that would be the difference of the two radius, the outer radius minus the inner radius, outer minus inner radius. And you also have here the product of the K, the thermal conductivity constant of this material, which your pipe is made of, and you have the area. But this time, class, the area, take note, is the lube mean area. The lube mean area. Miss, ano na ang lube mean area? Area 2 minus area 1 divided by the ln of area 2 divided by the ln of. So you have the quotient of area 2 and area 1. Now, where do you get this area 2 and the area 1? So this is your this is how you compute for area 2 and area 1. If you have a cylinder, I'm not sure if you have a solid mensuration class in senior high. If you have a cylinder, your area for heat transfer is to be viewed to be the face of that cylinder. If it's cut through the center, class ng angguan niya, the rectangle na siya. In short, I'm saying that the area that we're speaking of in here is the 2 pi r L area. The circumference of the circle, this circle, and the length of this particular cylinder. So that will constitute the area equivalent to that of a rectangle. The 2 pi r area could be changed to pi d. It could also be pi dl. It's the same thing. So you will have the area, the outer area, this one, that would be your A2, and you have your inner area, which is, I'm sorry about that class ha, my grade 2 ko di sa class sa kwarto. So you have here your area 1. So 2 pi R2L For area 2, 2 pi R1L for area 1. So that would be the areas that you see here. And you have the Ln of those two. And you place it here. That would solve for the rate of heat transfer. You have, or you can use another form of the formula wherein you have already the Ln of the two radius, the outer radius minus the divided by the inner radius, and then that's the Ln of the quotient of the two, then you divide by 2 pi kl. So you have the choice between using this particular raw formula where you need to first determine the A-log mean formula, or you can use this particular formula taken from these two areas in log mean form and this radius in log mean form. So you can use this other formula as well. Now, it could, this particular formula, which is this prior to substituting or determining the Q here, will give you the same answer when you use this particular formula in here. So duha ka bilog, either this one or this one. Set of formula. Ang lain ng siniho kay solbon mo anay ang lugmin area. This one. And then substitute it here. Then solve for the Q. But this one is more direct. So uses the R's already directly, the thermal conductivity of the material and the length of the pipe or the cylinder where conductive heat transfer is to occur. So this is your heat transfer rate or conductive heat transfer in a cylinder. So we have this particular sample problem for an application of this. Okay. For this sample problem, you're given a tube of 60 mm outer diameter insulated with a 50 mm layer of silica foam, for which the conductivity of is 0.055. Now followed with a 40 mm layer of cork with a conductivity of 0.05. So this one is 0.055, this one is 0.05. If the temperature of the surface, the outer surface that is of the pipe is 150 degrees Celsius, and the temperature of the outer surface of the cork is 30 degrees Celsius, calculate the heat loss in watts per meter of pipe. Okay, let me just pause this for now. My background ako, Abi. So now, we go to the next slide, which will give us the solution to this problem. So a tube, the outer diameter of the tube is insulated with silica. After that silica, you have another insulation in the form of a layer of cork. So the tube, the silica, and the layer of cork for our cylinder. So let's see how this particular problem is to be solved based on the required information, and that is the heat loss in watts per meter length of pipe. This one already tells you that your computation for the heat loss should be per meter length of pipe, which tells you you are to assume that your computation will use 1 meter length of pipe. Okay, so let's go to the next slide. So for A, so the solution is we have to have, we need to rather, in this case, I set silica as A and cork as B. So for A, this is our log mean radius class for us to be able to use the formula here of the log mean radius, this one. Now, for A, we have the log mean radius as 80 minus 30 divided by Ln of 80 minus 30. So you may wonder why it's 80 minus 30. So take note that silica is A. So let's go back to our problem why it's 80 minus 30. By the way, class, if you see here an 80 minus 30, automatic in the denominator, you will also see such value. So you will have also ln of 80 divided by 30. So question, why did we have the 80 and the 30 there? For A, which is for silica. So take note that your tube is 60 mm and it is insulated with a 50 mm layer of silica. So your silica in itself, the thickness of that is 50. The outer diameter of your tube is 60. So let me annotate here so you could see. Let's say this is your tube. And this is the center of our tube. Now, the diameter of your tube is outer diameter, that is stated here, is 60. So from the center, it's in terms of radius, that's 30. Now, I will add the next layer, which is silica, which is 50 mm. So if I will have another circle here, I have difficulty drawing a circle class pasensya. So you have this one. So you'll see that I have this one, this thickness of silica. So that's 30 plus this 50, that would be the 80. The 80, the radius 80 measured from the center of the pipe. So the radius of the pipe plus the thickness of the silica, that would be the 80, divided by the inner radius, which is 30. So that explains why, I'll just keep it there, class. That explains why you see an 80 minus 30 value here for the lugmin radius for the silica only, the first layer. Okay, you have 80 and 30. Now, what about the cork? So, ang cork, if we go back to the problem, the cork is 40 mm. So, 40 mm thickness. So, you have already 80. We have to add another layer for the cork. I'll just draw, class, this one here para hindi na ako mag-drawing ng perfect, kay ka-perfect, it's a circle. So you have this one. So this is your cork. This is another 40. So your 80 plus 40, that's 120. So if you go back to our next slide, so you have here 120. Now, your R for the B, your inner radius for the B, it's as if you're starting here is 80. So this is the lugmin radius for your cork, which is your B material. So 120 over 80. In this particular process, you have determined the lugmin radius of the two insulating materials that insulated your pipe. So your silica and your cork. Now, we determine next the heat transfer rate in A and B separately. So what is the heat transfer rate? You see here the thermal conductivity and the lugmin area. You can also place it here in the denominator. So you have XA over the product of K and A, which is the resistance due to material A, which is silica. And you have the driving force here, the temperature difference between the shall I say this one, the boundary between your silica and your cork in that case. So you have, by the way, class, wala na butang di ang lugmin area. Ginsulat lang din ako ang lugmin radius, but I have not written the lugmin area. So where will you get the lugmin area for A only? Because we're determining the rate of heat transfer in lugmin, in A, material A. This is the formula for A lugmin when you use, let me just clear this one. When you use the radius formula. So this is your, this one, the lugmin area. Once you have already determined the lugmin radius, you can determine the lugmin area in terms of that particular material. In that case, that would be silica. So a different route in solving the problem, determining the lugmin area based on the lug mean radius. I'll go back to the problem, to the solution rather. You have it here written that your lug mean area is 2 pi r, or your r lug mean times the length of the pipe. So that's where this is the source of that particular formula here. I have written it also in here. Okay, you have everything substituted, the thermal conductivity of silica, you have the value of the lug mean area based on this one, the lug mean radius, and you have T sub I minus Tx. And then you have for B, the same thing, but you change the thickness. The thickness, by the way, these are the thickness of the material. You change also the conductivity, and you change also the lug mean area based on the lug mean radius for material B. So it's patterned in the same manner as you have determined your Q sub A. So your Q sub B, you just change the given. So you have Tx, Ti, and To. What are this? So you could see, by the way, class, the value of this one, ini siya, nga may L lang, because this is per unit length of pipe. Or in this case, since our units is in SI, so you can say 1 meter length of pipe later. And this one, the 0.7748 would be these values multiplied, and then you have division here. So this is the simplified form. And you have the T sub I minus T sub X, and you have the T sub X minus the T sub O. T sub I is inner temperature. That's in the inner part of your pipe. T sub O is the outer temperature, meaning that would be the outermost part of your pipe, which is now the outermost cork. I think that's the cork already. The T sub X is the boundary between your cork and your, what's the material? The cork and the silica foam. Okay? So that would be your T sub X. Inner temperature, outer temperature. This is in the boundary of your foam and your cork. So you have T sub I minus Tx being equal to 2.839 Q sub A over L, and you have T sub X being equal to T sub X minus T sub O being equal to 1.291 Q sub B L over L. So this Q sub A and this Q sub B are the Q sub A and the Q sub B that you see here. Ang gwa na class, gin-rearrange lang siya, gin-bilin, ining mga temperatures dire, kag ining duha nga ini, gin-over sa duha ka Q. So you have Q sub A divided by 0.3522 L will be this one. 2.839 Q sub A over L to give you the difference of these two temperatures. Your Q sub B divided by 0.7748 L will be this 1.291 Q sub B over L to give you T sub X minus T sub O. Now, why have these two equations in the first place? Okay, so the question will be answered by the question that actually requires us to do what we need to do. So you're asked to determine the heat loss in watts per meter of pipe. So that is the requirement, the heat loss per meter length of pipe. Now, is this heat loss that we're talking about the same as, anyway, nagbutang ko na di siya, the same as in the pipe, in the foam, and in the cork? So we started with the discussion of conductive heat transfer, that if we have a series of resistances, the amount of heat transferred in each of these resistances or in each of these materials have to be equal. So what's done in here is that your QA and your QB would be equal to the Q, which is also the amount of heat that transferred through the pipe itself. So in that case, if you have these two equations, if QA and QB are said to be equal, then they can be equated since they are equal. So we have 4.3 adding 1 and 2 rather. So you have 4.13 Q over L is equal to T sub I minus T sub O. Now, I have a question, by the way, because I haven't asked a question in the beginning. Why add 1 and 2? This is your equations 1 and 2. If I may ask, why do you need to add these two? If the amount of heat transferred QA and QB are equal, so they can be equated, QA is equal to QB. In the solution here, we did not equate anything, but rather we added the two equations. These equations 1 and 2. What do you think was their addition of these two equations?
To take into consideration, Miss, the outer and the inner temperatures.
To take into consideration the outer and the inner temperature, which is actually what? If you take into consideration the inner and the outer temperature, with adding equation 1 and 2 give you the specific values of the inner and the outer temperatures? Okay, let me rephrase my question. 1 minute. Why do you need to add the two equations in the first place? If we go back to the question is asking if the temperature of the outer face is 150 and the temperature of the outer surface of the cork is 30, our outermost part in our series of resistances is 30, calculate the heat loss in the pipe. Now we say that the heat loss in the pipe, as discussed in principle, will be the same whether we're talking about the pipe, the foam, and the cork. Now, why is it that, I will not show the next page for now, why is it that you have added these two in the first place? Nga gin-add mo sa equation 1 kag 2 if we're after the Q. Why add these two? Why add T sub I minus T sub X being equal to this, equal to, or why add this one to Tx minus T sub O, which is equal to this? It's just like, I'm about to say the answer. It's just like what? When I add these two, when I add T sub I minus T sub X to T sub X minus T sub O, what is the expression resulting when I add?
The driving force.
The driving force, correct. So we are getting the driving force, which is actually not the T sub I, not the T sub O, but rather the difference between T sub I and T sub O. Do we know these two? Kabalo na ta sinisang T sub I and T sub O. Does the problem give us the value of the T sub I and the T sub O in the first place? Ginhatag na sang problem ang T sub I and T sub O. The answer is? The answer is yes. Ginhatag yan na, oh. 150, ang cork is 30. So actually, ang inner temperature mo is the 150 and the T sub O is the 30. So you have added these two. You add these two because you know the difference of T sub I minus T sub O. Anyway, so that we will not lose any time. So you add the two. If you add these two, i-add mo gining duha, right? I-add mo ning duha. Now, why mi i-add mo sila nga duha? Kay isa si QA, isa si QB. Isn't it that Q sub A is equal to Q sub B? So literally, you can add the two. You can simply change the QA and the QB to Q because anyhow, it's just the same for whichever material we're talking about, the pipe, the foam, and the cork. So you have 2.839 plus 1.291. That would be the value that you are seeing here, the 4.13 Q over L, because we have represented the QA and the QB as Q. This, I have question, is this already given in the problem? I said yes because you are given the inner temperature and the outer temperature of that of the cork, which is 120. This gives you already the rate of heat transfer per meter length of pipe. So you need not really find the length of the pipe, but you will express your answer in terms of per meter length of pipe. So this is already the answer to this particular problem. An application of Fourier's law to a geometric figure, which is that of a cylinder. So, and then this particular cylinder constitute a series of resistances, that for the foam and the cork. Okay? Any question? Any question, class?
None, Miss.
So if there aren't any question, there are still two topics here, that of the sphere and for conduction in parallel. So tomorrow, class, I'm on leave, and tomorrow you will have your dry lab schedule for 3 hours. So what you're going to work for tomorrow are problems only that can be solved up to the topic of the cylinder. The other problems that you cannot solve because I haven't yet discussed the concept of heat transfer through a sphere and that for parallel materials, that will have to wait. So ang inyo lang ma-answeran for tomorrow is ang inyo lang answeran. So ang hindi pa ma-answeran, leave it for that for the next time in which I can finish the discussion of these particular two concepts. Is that clear? I think I did not set the deadline tomorrow for the submission of the problem set in relation to conduction. If I did, I will moderate, I will edit the deadline because I have not yet discussed the part of the sphere and that of the parallel resistances, materials in parallel. Since that problem set already is the entirety of the problem set for the topic of conduction, it will have to wait until I'm done with the last two subtopics under conduction. Is that clear, everyone?
Yes, Miss.
Okay, I will stop
Yes,
sharing
miss.
now. I will stop sharing for now. I will check first, check my canvas. Wait, class. Under your modules, for conduction, you have problem set. Okay, I have set it on tomorrow. Let me check the problem. Wall, flat slab, a furnace, series, pipe, okay, this is actually wala siya sang problem diri nga sphere sa problem set. But nonetheless, this is a group assignment. 1, 2, 3, 4, 5, 6. I have placed 6 problems here. So you can start working on it tomorrow. I will moderate the submission of this particular quiz on the asynchronous time. The other time, aside from tomorrow, I will check in my load what is the other asynchronous time for ECHE 107. So I will change the deadline was set tomorrow to that particular time because of the number of problems that you need to process. Anyway, they are sample problems, class, in Gen 2 please also. So may guide ka muna. Kagdamo ako sa sample problems na ginbutang mismo sa lesson parts ng conduction, which you can use as the basis. That will guide you on how you're going to determine the unknowns in the problems I place in the problem set. If you have questions, you can still message me anytime since I haven't yet placed my consultation hours, my specific consultation hours. But class, tomorrow I'm on leave, so you can message me on Thursday or on Friday. But I will nonetheless change the deadline of submission for your problem set in conduction, which is not to be tomorrow because there's 6 problems that I have placed in there. Okay, so any question for now? Anyone? I know you're hungry. I too am hungry. Kaya lang alang